The James Webb Space Telescope is rewriting the laws of the cosmos. And the strangest part? It keeps finding things that simply shouldn't exist. Carbon in a universe barely 350 million years old. Galaxies that grew from nothing into giants almost overnight. So massive, they're known as universe breakers. And black holes 10 times bigger than their own galaxies, showing up before galaxies even have time to form. These are just the opening moves in a countdown of cosmic rule breakers. Each one shatters what textbooks call impossible, and experts can't explain how any of this is real. By the time you reach number 1, you'll wonder if we understand the universe at all. Are you ready to question reality? Carbon wasn't supposed to be there. Not so soon, not in that much quantity, and definitely not just 350 million years after the Big Bang. Yet that's exactly what Francesco D'Eugenio and his team at Cambridge found. Carbon signatures lighting up the spectrum of a galaxy from an era when, according to every textbook, only hydrogen and helium should exist. The detection came from Webb's near-spec instrument, which picked up spectral lines no one expected to see in such a young universe. Carbon, the backbone of all known life, showing up less than 3% into cosmic history. The numbers don't add up. For carbon to appear this early, the first generation of stars, population 3, would have had to live, explode, and scatter their guts at a pace that makes our Milky Way look sluggish. Standard models predict those early stars should have produced mostly oxygen, but the data flips that script. D'Eugenio summed it up. We were surprised to see carbon so early in the universe, since it was thought the earliest stars produced much more oxygen than carbon. If these stars really did churn out carbon this fast, it means the ingredients for planets, for dust, for chemistry were in play hundreds of millions of years ahead of schedule. That's like opening a bakery and finding a cake already baked before you even buy flour. The implications? Maybe the early universe was better at making the stuff of life than anyone thought. Or maybe the first stars lived and died in ways no one has modeled yet. Either way, if carbon can show up this soon, what else is hiding in the cosmic pantry? Because the next discovery isn't about ingredients. It's about entire galaxies that shouldn't fit in the oven at all. Jade's GS Z14-0 doesn't just break the rules, it blows right past them. This galaxy sits at a redshift of 14.3, which means its light has traveled for more than 13.4 billion years to reach us. In cosmic terms, we're looking at a galaxy that existed when the universe was less than 300 million years old. The surprise isn't just how far away it is, it's how big and bright it's already become in such a short time. By every model, galaxies at this age should be tiny, dim, and struggling to get organized, like toddlers just learning to walk. Instead, Jade's GS Z14-0 is shining with the power of billions of suns, showing off a structure that rivals much older galaxies. The numbers don't fit. For a galaxy to be this massive, this soon, it would need to form stars at a rate that makes the Milky Way look like it's stuck in first gear. The brightness levels are off the charts for anything at this distance. Astronomers expected faint smudges, not this cosmic spotlight. It's like finding a fully grown redwood in a patch of dirt where you just planted the seed. No wonder researchers started calling these finds universe breakers. Theories have scrambled to keep up. Some suggest ultra-fast star formation, others hint at hidden black holes, or even unknown physics. But nothing lines up cleanly. For now, Jade's GS Z14-0 stands as proof that the early universe was building on a scale and at a speed that no one saw coming. And if galaxies could grow this fast, what was fueling their engines? Because the next anomaly isn't about size, it's about what's lurking at the heart of these newborn giants. Sears 1019 rewrites the cosmic script. This galaxy, spotted just 570 million years after the Big Bang, isn't remarkable for its size or its stars, it's what's sitting at its core. Webb's spectrum revealed a supermassive black hole, weighing in at about 9 million times the mass of the Sun. That's not the shocker. The real twist is the ratio. This black hole makes up nearly 10% of its entire galaxy's stellar mass. In the modern universe, black holes usually account for a fraction of a percent. Here, it's as if the tail is wagging the dog. For decades, astronomers assumed galaxies formed first, slowly building up stars and gas before eventually nurturing a black hole at their center. But Sears 1019 flips that logic on its head, raising a cosmic chicken and egg problem. Did this black hole seed the galaxy around it, or did it somehow balloon to monster size before the galaxy had a chance to catch up? Standard models can't stretch that far. Even with the wildest growth rates, there just hasn't been enough time since the Big Bang for a black hole to reach this mass unless it started out enormous or fed at rates that break the rules of physics. Researchers are still reeling. Some suggest primordial black holes, remnants from the earliest instance of the universe, might have served as seeds, bypassing the slow path of ordinary star death and collapse. Others wonder if we're seeing the aftermath of supercharged, short-lived accretion bursts that only happened in the universe's unruly youth. Either way, the numbers don't fit. Sears 1019 isn't an outlier either. Webb keeps finding these heavyweight black holes in galaxies that shouldn't be able to support them, hinting at a universe where the usual order of operations just doesn't apply. And if the engines at the heart of these galaxies are this powerful, what else are they capable of transforming? Ever since Webb started sending back its deepest images, astronomers kept spotting something odd. Tiny, blood-red specks scattered across the early universe. These aren't galaxies in any familiar sense. They're little red dots, or LRDs for short, and they pack a punch far beyond their size. The numbers are staggering. Over 300 LRDs have been cataloged so far, most clustered between 600 million and 1.5 billion years after the Big Bang. Then, almost as quickly as they appear, they vanish from the cosmic record. The population curve isn't gradual, it's a spike in a cliff. That's not an observational glitch. Multiple independent surveys, using different fields and selection methods, all find the same sharp rise and fall. It's as if these objects had a brief window to exist, then faded out of the universe's script. Theories run the gamut. Some say LRDs are the dying embers of supermassive stars. Others point to black holes growing behind thick veils of dust. But every model faces the same wall. Why do they show up in such numbers for only a billion years? And why do they disappear so completely? Fabio Pacucci summed up the mood. This is pretty much all astronomers know about them. For now, the LRDs stand as a vanished population, a cosmic ghost story written in infrared. And if entire classes of galaxies can blink in and out of existence, what else could be hiding in those ancient shadows? GS-NDG-9422 doesn't just break expectations, it scrambles the rules of how galaxies are supposed to shine. At a redshift of 5.94, about a billion years after the Big Bang, this faint, compact galaxy stunned astronomers with a spectrum where the glow from its gas outshines its stars. Not just by a little. The nebular emission is so dominant that the usual stellar continuum is all but drowned out, flipping the script on what's normal in galactic physics. The numbers are wild. To power this kind of gas emission, the stars inside would need surface temperatures over 80,000 degrees Celsius, nearly double what's seen in even the hottest O-type stars today. Standard models can't keep up. Plug in any reasonable mix of star ages and masses, and you still fall short by a factor of 10 on the ionizing photons needed. The ultraviolet spectrum drops off sharply at 2,431 angstroms, a feature that can't be matched by ordinary stellar populations. Some teams tried to explain it with a hidden black hole or a dense shroud of hydrogen, but the data keep pointing back to something more extreme. Either this galaxy is packed with stars so massive and hot they barely exist in the modern universe, or it's hiding a power source we haven't seen before. Alex Cameron, who led the discovery, put it bluntly, "That's weird," and the theoretical models agree. If galaxies like GS-NDG-9422 were common, the early universe was a far more energetic, chaotic place than anyone imagined. But if this is a rare phase, it's a snapshot of cosmic chemistry running at full throttle, stars burning hot enough to light up the gas around them like a neon sign. And as astronomers scramble to explain it, the next twist is waiting in the spin of the galaxies themselves. Galaxies aren't supposed to prefer one direction over another. Yet, in a sample of 263 early galaxies from Webb's JADE survey, the numbers break the cosmic coin toss: 158 spin clockwise, only 105 counterclockwise. That's a 60-40 split, not the even odds demanded by the standard cosmological model. The odds of this happening by chance? Less than 1 in 150. The analysis, run through computer algorithms to eliminate human bias, holds up even when the data is mirrored or re-examined. This isn't a fluke of one patch of sky. Similar patterns have surfaced in other deep fields, hinting at a universe with a hidden axis, a built-in preference for spin baked into its earliest structures. The cosmological principle, the idea that the universe has no preferred direction, sits at the foundation of every modern model. If galaxies are born with a spin bias, that foundation cracks. Theorists have started to wonder if we're seeing the imprint of something even more fundamental, like a relic from cosmic inflation, or the signature of a universe shaped by forces we haven't yet mapped. No direct answers, just a growing sense that the cosmos may be less random, more structured than anyone dared predict. As one researcher put it, if this holds, we're going to need a new map. The James Webb Space Telescope has gathered evidence of galaxies forming just 350 million years after the Big Bang. Supermassive black holes make up 10% of their host galaxy's mass, and 263 distant galaxies show a 60-40 spin alignment that cannot be explained by current models. Astronomers have documented little red dots, vanished populations of galaxies that existed only between 600 million and 1 billion years after the universe began, and found cases where nebular gas outshines the stars themselves. Despite hundreds of peer-reviewed papers and the release of thousands of Webb images, scientists have not resolved how these anomalies fit into accepted theories of cosmic evolution. Nobel laureate Adam Rees has stated that these findings challenge the foundations of modern cosmology. As of today, the most precise models cannot account for the full weight of Webb's discoveries. What remains clear is that every new image from Webb is rewriting the timeline of the universe, and the search for answers is only just beginning.